Hi students, welcome to physics class. In this video we will discuss about the projection of uniform circular motion on the diameter is SHM, that is simple harmonic motion. First of all, we have to know what is simple harmonic motion. It is defined as the to and fro motion of the particle about a fixed point such that the acceleration is directly proportional to its displacement but opposite in direction is called as simple harmonic motion. This statement mathematically can be represented as A is directly proportional to minus y, therefore A is equal to minus omega square y. Now let us consider a circle as shown in the figure of radius A. Along this circle, a particle is rotating. The instantaneous position of the particle is P. The projection of particle P is drawn to y dash axis and the point of projection is N. N is the point of projection. From the figure, the angular displacement theta is same at O and at P. The distance from N to origin is y. This y is called as the displacement of the projection on the diameter. Now we have to understand how the projection of the particle moves when the particle completes one rotation along the circle. To understand this motion of the projection, please watch this video clip carefully. In this video, we have taken the projection of the particle along the circle at different points, and we have to observe how the projection, the point of projection moves when the particle completes one rotation. It is clear that it moves to and fro about the origin along the diameter. Next, we have to prove this motion of projection on the diameter is simple harmonic. Therefore, from the triangle OPN, by applying sin theta, which is equal to opposite side by hypotenuse. From the figure, the opposite side is ON divided by hypotenuse is OP, which is equal to ON is Y, OP is A. Therefore, sin theta is equal to Y by A. That implies Y is equal to A sin theta, which is equal to A sin omega t. What is omega here? Omega is the angular velocity, which is equal to angular displacement by time. Therefore, angular displacement is equal to omega t. Now we have derived the displacement of the rotating particle. Next, we have to calculate the velocity of this rotating particle. We know that the velocity is equal to rate of change of the displacement of the particle. So, velocity v is equal to dy by dt. Here y is the displacement of the rotating particle. And we have to differentiate this displacement with respect to time, which is equal to d by dt of y. Y is the displacement, which is equal to a sin omega t. While differentiating with respect to time, the terms which does not consist the time or constants, so we get a into d sine omega t divided by dt. Now again differentiating sine omega t with respect to t, we get a into cos omega t. The differentiation of sine omega t is cos omega t into omega, because d omega t divided by dt value is omega. The differentiation of d omega t is omega, which is equal to a omega cos omega t. Therefore, velocity of the particle is equal to a omega cos omega t. Next, we have to calculate the acceleration. We know that acceleration is equal to rate of change of velocity, that is a is equal to dv by dt. Here v is the velocity of the particle, which is equal to a omega cos omega t. By substituting v value here, we get d by dt of a omega cos omega t. The differentiation here is with respect to time, so the terms which does not contain time are the constants, so a omega into d by dt of cos omega t. The differentiation of cos omega t with respect to time is minus sin omega t, and we know that d by dt of omega t is omega, so we have to multiply with omega. Therefore, acceleration of the particle a is equal to omega into omega square, therefore minus omega square sin omega t. Replace this a sin omega t with the displacement y, then we get a is equal to minus omega square into y. Finally, we have derived the condition a is equal to minus omega square y, which is the condition for the simple harmonic motion. Hence, we can say that the projection of uniform circular motion on the diameter is simple harmonic. Thank you.